Hey everybody, it's Dan from SageMathTutoring.com once again with a test prep video for contemporary mathematics. And in this video, we're going to go over apportionment and the problem of apportionment and the various methods of apportionment and so on. So as usual, we'll play off of this outline here. And I also brought in these flowcharts that we could refer to as we go. So let's begin with the first part, which is the problem of apportionment in general. So what is the problem of apportionment in general? Well, basically, apportionment is when you're attempting to divide objects up that are themselves indivisible. So what do I mean by that? Basically, if you look at the key concepts flowchart, the problem of apportionment says that there are objects to be divided like seats in Congress. So let's say we've got 100 seats in Congress, something like that. 100 seats. And unfortunately, each of these seats cannot themselves be divided. A seat is just a seat. There's not a such thing as 0.5 of a seat and so on, right? So the seats themselves can't be divided, but proportionality criterion is to be fulfilled. So for example, larger states, let's say we have a country, let's say we even had a country like America, and we'll just take into account the mainland. It kind of looks like that. And imagine that, America really only had 5 states. So that's 1, 2, 3, 4, 5, right? So imagine America only had 5 states, 1, 2, 3, 4, 5. And there's 100 seats in Congress, but this state only has, 1,000 people. This state has 5,000 people. This state has 10,000 people, and so on. So there's a different population for each of the states. So the question is, we want to make sure that there's a proportionality going on where, the smaller states wouldn't have as many seats in Congress as the larger states. Okay, so proportionality needs to be fulfilled. The objects themselves are not divisible. I'd already touched upon that. And also, the question is, how can you fairly divvy out objects without privileging some groups, such as states, and undermining others? So what you'll come to see in this video is that it's difficult, if not entirely impossible, to be completely fair with regards to how many seats in Congress each state should get. All right, that's going to become clear as we go. Before we get into the nitty-gritty of all that, I'd like to get through the rest of this first flowchart and take a look at the key concepts in general. So we already covered the problem of apportionment. It basically has to do with the fact that there are multiple objects to be divided. The objects themselves are not divisible. There's proportionality criteria to fulfill, and there's also the question of how can you divvy the objects out in such a way that is fair. Another key concept is the idea of states in general. So we typically, think of the word states as applying to states in a country, but this term could be used for other categories as well. Seats, such as the seats in Congress. Seats are essentially the objects that are to be divvied out. The populations, well, that has to do with, the entire population of the country in general, but also the populations of the state itself. So, for example, one of the states, like, Alabama in the United States, that, of course, has its own population, as opposed to Texas having a different population. And then there's the standard divisor, which is the total population of the entire country divided by the total number of seats. So imagine that the United States as a country, I'll even write that, the entire country has a population of, let's imagine it was 5,000 people, which obviously is incorrect. But imagine that the entire country had 5,000 people, and imagine we had 500 seats in Congress. And in order to figure out what the standard divisor is, you have to take that population of 5,000 and divide it by the amount of seats that you have. So the standard divisor in this case would be 5,000 people. Again, that is the population of the entire country divided by the number of seats in Congress. And essentially what that tells you is, well, first of all, let's get clear that that would be 10. What that tells you is how many human beings each seat in Congress represents. So each, single seat in Congress represents 10 human beings. Okay, that's the idea of standard divisor. And then there is the concept of the standard quota. Now, the standard quota is the state population divided by the standard divisor. So once again, let's take a look at the previous numbers that I had. So as we had mentioned before, we could say that the total population, I'll call it total population of the U.S., is 5,000 people. We could imagine that. The total seats in Congress are 500. The standard divisor is 10. Now, once again, the standard divisor is calculated by dividing the total population of the country by the total number of seats in Congress. And once again, the standard divisor lets you know how many human beings each seat in Congress represents. So each seat in Congress represents 10 total human beings. So that's a way of thinking about it. Now we're moving on to the next concept, which is the standard quota. And the standard quota is as follows. It is the state population, the state population divided by the standard divisor. Now, imagine we were thinking about Alabama. And imagine Alabama has 111 people. All right, obviously, it's not true. Once again, we're just making this stuff up on the fly. Alabama has 111 people. So in order to get the standard quota, you would have to take 111, which is the state population, and divide it by the standard divisor, SD, which is 10. And that gives you the standard quota. Now, at the end of the day, that would end up becoming 11.1. All right. Now, the question is, of course, what does 11.1 mean in this context? Well, basically what it means is once you've figured out the standard quota, you now know how many seats in Congress each state should get. So Alabama, since it has 111 people as a population, Alabama should therefore get 11.1 seats in Congress. That's essentially what it means. Now, some of you at home watching probably realize we already have a little bit of an issue with the fact that there's this decimal here. There's a such thing as 11 seats in Congress. There's a such thing as 12 seats in Congress, but there's no such thing in reality of 11.1 seats in Congress. And again, that is a callback to the original problem of apportionment, where we made it clear that the objects themselves are not divisible. Seats in Congress are not divisible. But nonetheless, you can see the usefulness of figuring out the standard quota because it gives you a ballpark, a general idea of how many seats in Congress Alabama should have. Now, I had mentioned 11 seats in Congress, and I had mentioned 12 seats in Congress, and that is directly related to the next concept, which is called upper and lower quotas. What do we mean by upper and lower quotas? Well, basically, it means just that. It means just what I was referring to before. So Alabama, let's say Alabama gets 11.1 seats in Congress. Well, the number that is just below that, this could be rounded down to 11, that would be the lower quota, and the number that 11.1, the next integer up from 11.1 is 12. Okay, so this is the lower quota, and 12 is the upper quota. Okay, so these concepts, even though at this point it's sort of just a matter of memorizing what this means and all that, you're going to see how these concepts really come into play in future examples. Okay, so once again, brief review of what we just discussed. There is just the general problem of apportionment, which says that there's objects to be divided. Those objects themselves are not divisible. Proportionality criterion is to be fulfilled. Large states should get more seats in Congress. Smaller states should get less seats in Congress, and so on. And the question is, of course, how can you fairly divvy out the objects without privileging some groups and undermining others? Okay, so that's what we're contending with regards to the problem of apportionment. The states themselves are the categories, the subcategorizations of the total population. In the case of countries, it would literally be states. Seats are the objects to be divvied out, the indivisible objects to be divvied out. And in this case, we're looking at seats in Congress. The populations have to do with the total population in the country, as well as the states themselves. The standard divisor is what you get when you take the total population of the country and divide it by the total number of seats in Congress. That essentially tells you how many human beings each seat in Congress represents. And the standard quota is what you get when you take each state population. We worked with only Alabama, but we could have done the standard quota for Texas. We could have done the standard quota for New Jersey, etc. But standard quota is when you take a state population and then divide it by the standard divisor that we had already figured out before. And that essentially tells you how many seats in Congress each state should get. And then finally, we have the upper and lower quotas. Once you find the standard quota, in the case of it being a decimal, the lower quota is the integer that is just before the decimal, and the upper quota is the integer that is just above the decimal. And that is a summary of these concepts. Okay, so now we covered the problem of apportionment. We also covered key concepts as well. So let's move on to looking at the various methods of apportionment. Okay, so we will begin with Hamilton's method. Okay, so Hamilton's method is as follows. And let's look at this flowchart. It's a different flowchart. All right, so what do we have here? We have Hamilton's method right here. So the steps involved are as follows. You calculate each state's standard quota, you give to each state its lower quota, and then you give the surplus seats to the states with the largest residues until there are no more surplus seats. Now, obviously, that's going to sound like a bunch of gibberish unless we bring it down to earth with a concrete example. So I'm going to present you a chart that denotes a possible apportionment issue. Okay, so imagine that the top row represents the states. We have state A, B, C, D, E, and F, and the bottom row represents the populations of each state. So obviously 1,646,000 people are in state A, and so on. And then we have the totals down here. Let's make note of the fact that 12,500,000 people right here, that represents how many people are in the country, right? So this is the country population. And these are the various state populations. Okay, so it's good to have these charts to work with when you're doing the Hamilton method, the Jeffersons method, and so on. So anyway, we're going to keep looking at the Hamilton method. So let's be clear, the Hamilton's method, like all these other methods, they are methods used to at least attempt to fairly assign a certain amount of seats of Congress to each state, depending on the population that the state has. Now, if we're to listen to the steps involved with the Hamilton's method, once again, we're going to be calculating each state's standard quota. So let's actually do that right now. Once again, the standard quota is what you get when you divide the state population by the standard divisor, right? State population by the standard divisor. Now we have the state populations here, but the question is, okay, well, what's the standard divisor? Let's figure that out, right? Now the standard divisor, as you may recall, is the total population over the amount of seats in Congress that you have. So In this case, the total population is clearly 12,500,000. Right, so we're going to write that right now. So that is the total population of the country. But the question is, how many seats in Congress do we even have to give out to the various states? And let's say that the total amount of seats that we're divvying out would be 250. 250. So therefore, the standard divisor will end up being 500,000 people. So in order to figure out the standard quota of each of the states, you have to take the population of each state and divide it by 500,000, and that would give us the following row. And really, I should say rows because I wrote an extra row here. But the row that I was referring to, at least for now, is this one right here. That's the extra one that's filled out at least. That's the standard quota row. So once again, we took each state population, we divided it by the standard divisor, and we ended up getting the standard quota, right? And notice how the standard quota, when you do it correctly, you end up getting the total amount of seats in Congress, like the literal amount of seats in Congress. In this case, it's 250. Once you add each of these standard quotas up, you should get exactly 250. Now, you may have noticed I made an extra row called the lower quota row, and the reason for this is because you definitely want to pay a lot of attention to the lower quota of each of these standard quotas when you're doing the Hamilton's method, which is what we're looking at right now, the Hamilton's method. And let's actually kind of think this through together and make sure that we're on the same page about it. So as I mentioned before, the lower quota is the integer before the decimal version of the standard quota. So 32.92, well, the integer before that is going to be 32. The integer before 138.72 is going to be 138. And this one's going to be 3. And this one's going to be 41. This one is going to be 13. This one's going to be 19. And then when you add all that up, what you end up getting is 246. 246. Now, what happened here? We have the state populations to take into account. We figured out the standard quota, so State A should basically get 32.92 seats in Congress. State B should basically get 138.72 seats in Congress. And when you add it all up, it adds up to the total amount of seats in Congress that you have. And what did we do? We rounded this down, each one of these down. You can think of it as rounding down. We brought it down to the integer that comes before the decimal version of the standard quota, and that's 32, 138, 3, 41, 13, blah, 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 blah. But this kind of highlights, the fact that this all adds up to 246 highlights the problem of apportionment. At the end of the day, if you kind of round these down to these integer values, you end up with a total of 246 seats in Congress that are assigned. You have 4 more seats of Congress that you have to give out to somebody, right, in order to get the full 250 seats of Congress. And that really highlights the problem of apportionment just in general, right? The question is, who do the 4 seats go to, right? The 4 extra seats, or we call them the surplus seats. Well, Hamilton's method, once again, as we had kind of talked about before, says the following. Hamilton's method says that we should give each state its lower quota. Well, we just did that. We assigned state A 32 seats, but now we have surplus seats, and we're going to give the surplus seats to the states with the largest residues until there are no more surplus seats. So, of course, the question is, what the heck do we mean by residue? Well, residue would be the decimal value that takes place after the decimal point. So in this case, for state A, the residue would be 0.92. The residue for state B would be 0.72, and so on. So I think it's going to be a good idea to actually write another row underneath here that just has the state residue. So I'm going to do that right now. So now we have a row that denotes the residues of each state, And again, 0.92, where did I get that from? Well, I got that from the 0.92 right here. Also worthy of note is the fact that when you add all the residues up, you should get 4.00 because that's how many surplus seats you have left over, right? So once again, according to the Hamilton's method, we're going to give the surplus seats to the states with the largest residues until there are no more surplus seats. So what does that mean? That means that we're going to do the following. We're going to give the extra seats to the states that have the largest residue. So since state A has that residue of 0.92, we're going to give state A the first one. Looks like state D has the next one. It looks like state F has the third one, and state B has the last one. So state D gets the second surplus seat, and state F gets the third, right? And finally, state B gets the last, or we could just call it the fourth. I'd rather call it the fourth. All right, and we'll do maybe a little divider here too. All right. So what happens at the end, therefore, as a result of divvying out the surplus seats in this way? Well, at the end of the day, we know for sure that we are going to have 250 seats, which, if that's not clear already, it's going to become clear soon. Basically, at the end of the day, state A no longer has 32 seats because we just gave state A an extra seat. So state A now has 33 seats. State D now has 42 seats. State F now has 20 seats. And finally, state B now has 139 seats. And this state C still has 3 seats, right? And state E still has 13 seats. Now, if we were to add all of these up after having divvied out the 4 surplus seats, now we're going to have 250 total seats in Congress represented if we were to add all of this up. All right, so we have just divvied out the seats of Congress according to the Hamilton's method, and that's how you do that. Now, similar to the mathematics of voting, the mathematics of apportionment is fraught with problems. So it is the case that there is no perfect method of apportionment in general, and I don't want to get too much into the details of the various flaws of apportionment. For the contemporary mathematics test, you do need to have a basic understanding of the paradoxes and flaws, however, and you're also going to need to know which flaws are violated by which methods. Okay, so that's important. So let's take a look at why the Hamilton's method is not perfect. Well, according to the flowchart, we can see clearly that Hamilton's method violates the Alabama paradox. It also violates the new states paradox, and it violates the population paradox. Let's very quickly just see what these paradoxes are about. So starting with the Alabama paradox. The Alabama paradox says that when an increase in the total number of seats being apportioned in and of itself forces a state to lose one of its seats. So in other words, imagine we had increased the seats from 250 to a larger number. The Alabama paradox says that, let's say you began with 250 seats in Congress, but now we added an extra seat, so now there's 251. Interestingly enough, the Alabama paradox is such that even when you increase the amount of seats to be apportioned, it's possible for one of the states to then lose a seat. That seems like it shouldn't be possible, but that's why it's a paradox. In other words, if this goes up to 251, it's possible that state F might go down to 19 and lose one of its seats. Now, I'm just going to expect you to simply memorize the fact. I'm not going to demonstrate the Alabama paradox in action, but I want my student and all of you students who are going to take this test to simply memorize the fact that the Hamilton's method will occasionally cause that to happen. Okay? And that's why the flowchart's pretty helpful. So the Hamilton's method will also occasionally result in the new states paradox. And according to the new states paradox, sometimes when a new state is added, as well as extra seats, it will cause a previous town to lose a seat they had before. All right. So what that basically means is, let's say we have states A, B, C, D, E, and F. Well, imagine we add another state called H. And not only that, but we also bumped up the seats to, let's say, 255, something like that. Well, that will cause occasionally some of these seats, or states rather, to lose a seat. Okay? So that's the new state paradox. Once again, the Hamilton's method will occasionally result in the new states paradox as well, which is one of the flaws of the Hamilton's method. And finally, the Hamilton's method also might result in the population paradox. And that says that when a state with a positive population growth rate loses one or more seats to another state with a smaller or no population growth rate. So in other words, imagine state A increases in population. Right now it's at 1,646,000 people. So imagine state A increases to, let's say, 2 million people, and state B actually loses some people or stays the same. The population paradox is when A paradoxically loses a seat, even though its population went up. And even if population B went down or stays the same, it will gain a seat. That's the population paradox. And once again, with the Hamilton's method, the method that we just kind of did, that can happen every now and then. And it has to do with the residues and, who gets the surplus seats based on the residue. Okay? So those are the three flaws with the Hamilton's method. So let's move on to the next method, which is, we'll put this off to the side, which is the Jeffersons method. So the Jeffersons method of apportionment has the following three steps. According to the Jeffersons method, you find a suitable divisor for D, which we'll explain. Number two, you use D as the divisor. You compute each state's modified quota. Notice how it's the modified quota now. Before it was the lower quota, but now it's the modified quota. And step three, each state is apportioned its modified lower quota. So basically what happens now is the following, and I'm going to demonstrate this with the same populations right now, but first I'll just erase some of this stuff down here. Okay, so we are going to adjust this chart so that we have two more rows to take into account, or two different rows, I should say. Two different rows to take into account. And that would be the row that has something called the modified quota. We'll call that the modified quota. I'll call it mod Q. And lower quota. In this case, I'll call it lower Q. And it's the modified quota as opposed to the standard quota. And it's going to be the lower quota as it pertains to the modified quota. And this will become clear in a moment. Let's remind ourselves of what was the problem that the earlier method, the Hamilton's method, was attempting to address. The problem was that we had 250 seats, and unfortunately, when we figure out the standard quota for each of the state's populations, you end up with these decimals. And due to the problem of apportionment, due to the fact that congressional seats are not themselves divisible, we ended up going with the lower quota here. And that was with the Hamilton's method. And the issue was that once we rounded every one of these little standard quotas down, we ended up with only 246 total seats, and we had an additional 4 seats to take into account. What the Jeffersons method says is that a better approach would be to find a different standard divisor that would result in larger standard quotas, larger numbers here, and then you would overshoot 250, and then you would round those larger numbers down to their lower quota in such a way that would result in 250 seats. So as a quick reminder, in case that's not clear, the standard divisor that we were using before with the Hamilton's method was 50,000. So I'm going to write that. The standard divisor, we'll call it the SD, was 50,000. So this standard quota is based on an SD of 50,000. But now what we're going to do is we're actually going to choose a different SD. And this really highlights the fact that you can do that. You're allowed to actually do that. As it turns out, apportionments do not have to be based exclusively on the standard divisor. So we are actually allowed to change this. And when we do so, for example, if we lower this, so for example, if we use 49,500 instead, I'll just write that down, 49,500, that's going to result in a different quota. Okay, so 49,500. By taking the old standard divisor and making it less, interestingly enough, that results in the modified quotas actually being larger than the standard quotas. And in case it's not clear as to why that's true, keep in mind that the standard quota is equal to the state population over the standard divisor. So this is the row that has the standard quota for state A. This has the standard quota for state B. This is the standard quota for state C, and so on. And how did we find these numbers? Well, we took the state population, which was 1,646,000, and we divided it by the standard divisor of 50,000. And I'll just put these in parentheses. So we took the state population and we divided it by the standard divisor of 50,000. Now, what happens when you make a denominator? Imagine this was 50,000. And what happens when we take a denominator and we make it smaller? When you make a denominator smaller, that makes the entire number get larger. So when you make a denominator smaller, that makes the standard quota larger. Okay? So what we've done by changing the standard quota from 50,000 to 49,000, what we're doing is we're now going to have a quota, a modified quota, that is larger than the old standard quotas. Now, to be perfectly accurate, we're going to refer to this new divisor of 49,500 as the modified divisor. We had the standard divisor from before, and we just modified it to 49,500. All right. Now, when we modify the standard divisor to a lower number, that once again is going to result in larger modified quotas when you compare it to the old standard quota. So I'm going to fill in the new numbers that belong in this row. Okay, so we have new modified quota based on a modified divisor. The old standard divisor used to be 50,000. We made that smaller, which, by the way, is what the Jeffersons method is all about, making the standard divisor smaller. So now it's 49,500. That enables us to have a modified quota. And let's look at the modified quota, especially when compared to the standard quota. So the standard quota used to be for state A 32.92, but since we changed the standard divisor so that now it's less, it's 49,500, the standard quota has increased to 33.25. And you will notice that all of these numbers, looks like this one got away from me. Let's make this guy a little smaller, and this goes right here. So all of these numbers actually increased. We went from 3.08 all the way up to 3.11. Over here we went from 138.72 all the way to 140.12, and so on. So you can very clearly see that each of these numbers, the standard quota, increased to a larger number, and now we are ready to actually round each of these numbers down. So the 33.25 just becomes 33, and the 140.12 becomes 140. The 3.11 becomes a 3. We get a 42 here, we get a 13 here, and we get a 19 here. And what has resulted as a result, is that when you add all of these up, it actually does end up becoming 250, and therefore we have taken into account all of the seats in Congress. Okay? So once again, if you're going to be doing the Jeffersons method, you come up with a new standard divisor that is such that when you use it, it actually bumps up the old standard quota until it's high enough. You actually have to bump it up so that it's high enough that is such that when you round it down, you end up with the sum of 250. Now, you might have the question, what modified divisor should I use? And unfortunately, it will just be a matter of trial and error. So if you're going to use the Jeffersons method, you find the typical standard divisor. First, really, you would just see if that would work. You just see if that would work, and it would result in standard quotas that add up to, or lower quotas that add up to 246. That's actually the Hamilton's method. But if it doesn't work, the Jefferson's method says take the standard divisor, make it less. That bumps up the modified quotas until they're a large enough number such that when you round them down, it will add up to 250. So that's the Jefferson's method. Okay, so let's take a look at the flaws of the Jefferson's method. So we just went over what the Jefferson's method is. Now we're going to look at what some of the flaws are of the Jefferson's method. And as usual, we're going to refer to the flowchart. So as you can see in the flowchart, the Jefferson's method can violate the quota rule. And by the way, This UQV means upper quota violations. Okay, that's what it means. And the Jeffersons method can violate the quota rule. And the question is, what is the quota rule? And let's take a look at what the flowchart says. So the quota rule and quota violations in general are as follows. A state should not be apportioned a number of seats smaller than its lower quota and larger than its higher quota. So for example, imagine you get a standard quota of 33.7. Let's say state A gets a standard quota of 33.7. And what that effectively means is that, in essence, state A should get 33.7 seats of Congress. Now, due to the problem of apportionment, that is, of course, not possible. But it's important to keep in mind that there is the lower quota, also known as 33, and the upper quota is the next integer above that. That's going to be 34. Now, a quota violation is when the quota rule is broken. And the quota rule says that, okay, I don't care if you use Hamilton's method, Jefferson's method, or whatever. At the end of the day, if state A has a lower quota of 33 and an upper quota of 34, it should be against the rules that state A ends up with an amount of seats in Congress that are less than 33 and an amount of seats in Congress that are more than 34. So in other words, if state A ends up getting 32 seats, that's bad because its standard quota was 33.7, therefore the lower quota was 33. Therefore, we should not give state A less than 33 seats. That would violate the lower quota. Similarly, state A should not get more than 34 seats. So in other words, you don't want to give state A 35 seats. That's too much because the standard quota for state A was 33.7, and it would be obnoxious to give state A 35 seats. To people who study the apportionment methods, that just seems very unfair. Okay, that's very unfair. So that's the quota rule. Basically, if a state gets a standard quota, at the end of the day, after applying whatever method, it should be the case that the state does not get less than the lower quota and does not get more than the upper quota. So that's the quota rule. Now, according to the flowchart, the Jeffersons method violates the quota rule because it can cause an upper quota violation. In other words, the Jeffersons method might end up giving a state a number of seats in Congress more than its upper quota. That can happen. That is something definitely worth memorizing. On the test, it might say, the Jeffersons method violates which rule, and in this case it would be the quota rule, and what kind of violation is it. You should know that it's going to be an upper quota violation. So that is something that is very important to know. Okay, so moving on to the Adams method next. So let's put an asterisk near the Adams method. And let's analyze that. So according to the flowchart, the Adams method is as follows. You're going to want to find a suitable divisor, this time raised a bit. So take note of the difference between the Adams method and the Jeffersons method. With the Jeffersons method, you found a suitable divisor that was lowered a bit. With the Adams method, you find a suitable divisor that is raised a bit. And some of you at home watching might understand immediately that that's going to result in the modified quota being lower than the standard quota. Step number 2 is to use D, the divisor, the new divisor, in such a way that you would compute each state's modified quota. And then step number 3, each state is apportioned its modified upper quota. So in a way, this Adams method is a sort of reflection of the Jeffersons method. Jefferson's method has you finding a suitable divisor that is lowered a bit. Adams' method has you find a suitable divisor that is raised a bit. The Jefferson's method has you computing the state's modified quota. Well, same thing with the Adams method. Although it's the case that the Jefferson's method will result in a larger modified quota when compared to the standard quota, the Adams method will result in a smaller quota when compared to the standard quota. The Jefferson's method says each state is apportioned its modified lower quota, and the Adams method says that each state is apportioned its modified upper quota. Okay, so let's see an example of that in action right now. Looking at our lovely chart. And when we look at the chart, which is slightly revised, what we once again see is the top row has the population of each state. And immediately, I didn't mention the standard quota for each state, but we're immediately getting into the modified quota for each state. Now, the modified quota in this row is based on choosing a divisor of 50,500. The old divisor used to be 50,000. So obviously, with this modified quota, we have bumped up the standard divisor so that it's a little bit larger. What that's going to result in is slightly smaller quotas. Now, for the record, you could always rewind the video to double check, but the old standard quota, based on 50,000, used to give us a 32.92 for A. For state B, it used to be 138.72. So we can see that this is a little lower now due to the new standard divisor. State C used to be 3.08, but now it's 3.05. So that applies across the board. The fact that we raised the standard divisor, that once again has the effect of lowering the quota a little bit. Now, according to the Adams method, you go ahead and find that new modified quota by dividing the state population by the new divisor. And in a way, it is a test to see if it will work. Here are the new quotas. And then what you do is you round up. So now that these are a little bit smaller than they used to be when it was the standard quota, now we're going to round each one of these up to the upper quota, and you end up with 33, 138, 4, 42, 14, and 20. Now, here's the thing. If we were to add all of these, it would end up giving you 251. Now, that is a problem because we want 250 seats in Congress, so we have too many. So what we need to do, therefore, is actually make the standard divisor, 50,500, a little larger. And what that will do is that will make each of these quotas even smaller. And then when we round it up, hopefully, we end up with a string of numbers that gives us exactly 250. So what we're going to do, since I knew that this was going to happen, we're going to try out a different divisor called 50,700. Once again, remember, the standard divisor for this whole country is 50,000, but we are purposefully choosing a number larger than 50,000 so that we end up with smaller quotas here. Okay? Now, as far as which number to pick, basically, once again, you just do trial and error. In fact, this whole section with this chart really highlights the occasional necessity of using trial and error. We first tried 50,500 Now we're trying 50,700. And when you do that, you end up with the following modified quotas. So you end up with these new numbers. Notice how these are smaller than the old modified quotas that we tried when the divisor was 50,500. These are a little smaller. So let's see if after changing these to the upper quota, we end up with the perfect amount of numbers. So this becomes 33. This becomes 137 because we're rounding it up. This becomes 4. This becomes 42, this one becomes 14, and this one becomes 20. So notice how just by bumping the standard, or I should say the modified divisor, up by 200 points, we got slightly smaller numbers. And this is the same as that. The upper quota here is the same as the upper quota here. Upper quotas here match, the upper quotas here match, and so on. But notice how by bumping this up, we were able to get this upper quota one less than 138, and that will definitely result in the sum of 250, which is the target amount since there's 250 Congress seats. That's how you do the Adams method. Once again, you choose a standard divisor or a modified divisor that is slightly higher than the standard divisor. That results in lower quotas than the standard quota. You then round up each time, and then you add it, and you see if you end up with the exact amount of seats in Congress that you need. If you end up going over, then you have to bump this divisor up a little bit. That would result in smaller quotas, all of which you would round up to the next integer. You then add it up again and see what happens. This time we got 250, and then we are done with that one. So let's take a look at some of the flaws that can occur if we're using the Adams method. So according to the flowchart, as you can see, the Adams method, it looks like we could have a lower quota violation. Okay, so that's one of the things, unfortunately, that could happen with the Adams method. You could end up with a lower quota violation. All right, so in other words, let's say that you have a modified quota of 32.7. If that's the case, then the lower quota is 32, and the upper quota is 33. So according to the quota rule, you shouldn't, whoever state has a modified quota of 32.7, whatever that state is, they should definitely not get less than 32 seats, and they should not get more than 33 seats. So the Adams method sometimes results in a lower quota violation, denoted by LQV, which means that occasionally, when you're using the Adams method, you might end up with a number like 31 as your final seats to be apportioned to this state, when basically the lower quota is 32, so therefore you're not quote-unquote allowed to go below that. It would be a violation to do so. And the Adams method will occasionally and unfortunately result in that violation. Yet another reason why these voting methods are imperfect. Okay, so let's move on to Webster's method. So we just covered Adams method, and now we're going to look at this one. And as per before, we're going to look at the flowchart first. So let's look at this flowchart. Webster's method. Let's see. The steps involved are to find a suitable divisor, which is code for the fact that it might require some trial and error. Step 2, you're going to use D, the suitable divisor, as the way to compute each state's modified quota. And then finally, step 3, you're going to find each apportionment by rounding each modified quota in the conventional way. Okay, so let's take a look at that. First of all, let's get clear what do we mean by rounding in the conventional way? Let's say we had something like 35.8. Well, most people know that if you were to round 35.8 in the conventional way, you would end up with 36. Because we know that if we're dealing with a number that has a decimal value of 0.5 or above, could be 0.6, could be 0.7, could be 0.8, could be 0.9. If we're dealing with a decimal value of 0.5 all the way up to 0.9, then we round it up. Whereas, as many of you know, if we're dealing with a decimal value of less than 0.5, such as 0.4, 0.3, 0.2, 0.1, then we're going to round it down to, in this case, it would be 35. So really, Webster's method is the exact same thing that we just did, only now the difference is the way that we round it. Hamilton's method has you rounding down to the lower quota, and then you base the divvying out of the remaining Congress seats based on the residuals. Jefferson method has you rounding down to the lower quota. Adams method has you taking the modified quota and rounding up to the upper quota, always by the way. And Webster's method has you finding a suitable divisor, going through the motions, and then rounding in the conventional way. So let's see what that one looks like in action also. Okay, so looking at this chart right here, once again we have the population on the top row for each state, all the way across here. And now we're going to look at the Webster apportionment, where you could always start with the standard quota, which is the quota that you would get when you use the standard divisor. And as you may recall from the first chart that we made for the Hamilton method, the standard divisor is 50,000, right? So what do? Well, we take the total population of the whole country, and then you divide it by the number of seats, which is 250. We're looking for 250 seats in Congress, so you add up the whole population, and then you divide the entire population of the entire country by the 250 seats, and that would give you 50,000. And what that basically means is each seat symbolizes 50,000 people. Okay, so then you go ahead and you find the standard quota, which is a matter of taking the state population and dividing it by 50,000. Okay, so the standard quota for country or state A is 32.92, and so on and so on. Now, when you have the standard quota, you should be able to add it all up, and you would get 250. Now, since we are doing Webster's method, we are now going to partake in conventional rounding. And as many of you know from grade school and all that good stuff, this would become 33. This right here would become 139. This would end up becoming 3 because you would round it down. This next one here would become 42. This one would become 14. And finally, this one would become 20. But the problem is that when you add all of these, unfortunately, you're going to end up with 251. So unfortunately, we have one more seat in Congress as a result of adding these than we want. We want 250 total seats in Congress. So we're going to have to make this number less. Now, the way to make this number less is to make these numbers less. Well, how could you make these numbers less? As you may recall from not too long ago in this video, you can make these numbers less by making these numbers less by bumping up the standard divisor. If you actually make the standard divisor larger that will result in a standard quota that is smaller. Okay? And that is exactly what this row is meant to represent. This is going to be a row for the modified quota with a standard divisor of 50,100. So we're taking that 50,000, we're bumping it up a little bit, and as a result, we should end up with smaller numbers. I'm still going to write it in green. And the smaller numbers end up becoming the following. You would end up with 32.85, which is slightly smaller than 32.92. You would end up with 138.44, which is slightly smaller than this, and so on. Now, when we round these in the conventional way, you end up with 33, once again. This one becomes 138, and right there, that could be the difference. This one becomes 3, this one becomes 42, just like above. This one becomes 14, just like the conventional rounding from before. And this one becomes 20. Now, as a reminder, we want 250 seats. When we did conventional rounding to the standard quota, we ended up with a sum of 251 seats. So the question is, what do we get when we add these after modifying the quotient? And this would actually, if you were to add it all up, this would indeed give you the 250 seats that you are looking for. All right? So once again, when it comes to the Webster's method, you might want to start with the standard quotient, right? Find all these numbers, round it in the conventional way, and then see if you end up getting 250. But if you get larger than 250, that means you have to take this standard divisor and bump it up. That will result in a modified quota, which will give you slightly smaller numbers. And then you round it in the conventional way again. You end up with these numbers, and we landed on 250. Now imagine, by the way, we had performed a modified quotient, and then we ended up with 249. Well, what that means is we would have to make the standard divisor a little bit less, somewhere in between 50,100 and 50,000. Maybe you could try 50,050 and then find the next modified quotient, round those, and hopefully you will eventually hone in on exactly 250 seats in Congress. Okay, so I hope that makes sense. Let's take a look at the flowchart to see what the problems are with the Webster method. So when we look at the flowchart at the Webster method, we see that the Webster method violates occasionally the quota rule. Okay, so it occasionally violates the quota rule, and it could violate it in such a way that would result in either an upper or a lower quota violation. Okay, so that's worth memorizing. The Webster method, which features conventional rounding, could indeed result in the occasional quota rule violation, either upper or lower quota rule. So let me make this a little bigger so you can see the relationship there. Okay, so that's how that works. Okay, looks like the Huntington Hill method is next. So, Huntington Hill method. I think it's worth saying right out the gate that the Huntington Hill method is the method that the United States Congress actually uses. Okay? It's possible that on the test they're literally going to ask that. So just recognize that the Huntington Hill method is the method of choice in that regard. So let's take a look at this one. Huntington Hill method. Right here, and the steps involved are to find a suitable divisor, D. You're going to once again use D as the divisor. You're going to compute each state's modified quota. That's basically what we've done before. But instead of using conventional rounding, now you're going to round according to the geometric mean. So right now, before we dive into an example, I think it's a good idea to get clear on what the geometric mean is of two numbers. Now, imagine we wanted the conventional mean of something like 7 and let's say 10. Well, by now, we know that that's going to be a matter of adding 7 plus 10 and then dividing by 2. And you would quickly come to find that that is 8.5. Okay, that is the arithmetic or arithmetic mean. But now we're going to look at the geometric mean. So the geometric mean is somewhat similar in a strange way, only instead of addition and division, it's multiplication and square root. So for example, imagine I wanted to take the geometric mean of, let's say 6 and 10. Well, all you have to do to take the geometric mean of these two numbers right here is to multiply 6 times 10 and then take the square root of that product. Now for the record, that would be the square root of 60, and that would simplify into 2 radical 15. Now you could always plug this into your calculator or even this into your calculator, and you would end up with a decimal, some interesting looking decimal. So that's how you find the geometric mean. Now the question is, now what do we mean by rounding according to the geometric mean? I mean, it's one thing to know how to find the geometric mean. It's another thing to know how to round according to the geometric mean. Well, once again, I'd like to refer to the conventional rounding method. Imagine you have two numbers that you're considering called 60 and 61. Well, if you were to take the normal arithmetic average or mean of these two numbers, you would get a special number called 60.5. And that right there is what we could call the cutoff point, where anything above, or anything, let's say 60.5 and above, would get rounded up to 61. Anything below 60.5, and in between 60, would be rounded down to 60. So the conventional rounding takes into account the arithmetic mean of the two consecutive integers. Once again, the average of these two is 60.5. That provides you with what we're going to call the cutoff point. Anything 60.5 and above gets rounded up to 61. Anything below 60.5 gets rounded down to 60. We are going to apply the exact same concept, only now we're going to use the geometric mean of two consecutive integers as the cutoff point. Now, when you're using the geometric mean as a cutoff point in order to know how to round a particular decimal, it's really, really helpful to have a chart, okay? Because you're not going to want to calculate the geometric mean all the time. You're going to want a chart that kind of has a list of the geometric means that might come into play. So here is a chart that you could use. So let's take a look at this chart. And you'll notice we have, of course, the lower quotas here, the upper quotas in this column, and the Huntington Hill cutoff, which, by the way, is the geometric mean. And they're nice enough to also give us the Webster cutoff, which is just the arithmetic mean that you're so used to. And you know that when it comes to the Webster cutoff, if you have anything from 1.5 or above, you're going to round it up to the upper quota. If you have anything less than 1.5, you're going to round it down to the lower quota. Well, here are the various geometric means of these consecutive integers, and this is the cutoff point. All right, so as you can see, having a chart of the cutoff point for the Huntington-Hill method is very, very handy, and it may very well actually come into play in the next example. So let's immediately look at an example of the Huntington-Hill method in action. And we're going to keep this chart handy right now. And imagine that we have an election that has the following results. So let's say you have all of these state populations here. It's a total of 400,000 people in the country. You have 40 congressional seats, and the standard divisor is 10,000. Therefore, the standard quota will be the following. Okay, now, according to the Huntington-Hill method, we're going to round these standard quotas according to the cutoff point. So, for example, this quota, 3.48, well, the lower quota, in this case, is 3, the upper quota is 4, and the Huntington-Hill cutoff, once again, based on the geometric mean between 3 and 4, is going to be 3.46. So this is above 3.46. So state A is going to get rounded up to 4. Looking at this next one, 10.51 for state B, that's the standard quota. And between the lower quota of 10 and the upper quota of 11, the cutoff point is 10.488. This is clearly above that, so this becomes 11. Looking at this one, we have 6.51. The lower quota is 6, the upper quota is 7. That's found right here. The cutoff point is 6.481, so therefore this one would get rounded up, and so on down the line. 14, lower quota 14, 14.02, the lower quota is 14, the upper quota is 15. That is to be found right here. The cutoff point is 14.491. Clearly that's less than that, so therefore that gets rounded down. Finally, 5.48, the lower quota is 5, the upper quota is 6. That's to be found right here. The cutoff point is 5.477. This is just above that, and therefore this gets rounded up to 6. And then at that point, when you add all of these, you end up with 42. So, as you can see, even with the Huntington-Hill method, you might end up, rounding all of these in such a way that results in this number being too large. Now, when that happens, similar to what we had talked about before, you're going to have to find a different standard divisor. Okay, now if it's the case that this ends up being too much, then what you have to do is make the standard divisor larger. So if it's the case that you end up with too many seats in Congress after rounding all of these according to the Huntington-Hill method, you then have to make the standard divisor larger. So that process of making the standard divisor larger, we could even just write Huntington-Hill. I'll write HH for Huntington-Hill. That process of making the standard divisor larger is a trial and error process. So what we can now do is come up with a different standard quota that is based on let's make the standard divisor a little bit larger. We're going to make it 10,030. So were you to use the standard divisor of 10,030, you would end up with the following standard quotas. You would get 3.47, 10.479, and so on. And now that we bumped up the standard divisor, these are each going to be a little bit smaller, and that's going to result in the rounding maybe being different. So let's find out. According to this chart, this one has a lower quota of 3 and upper quota of 4, so that is found here. 3.464 is the cutoff point. We are above that, so therefore this will once again be 4. looking at this one right here, we have 10.47 over here. 10.488 is the cutoff point, and we are now below that. So that's the difference between, what happened this time and what happened last time, right? Before we got 11, now we have 10. So that's a good sign. 6.491, lower quota is 6, upper quota is 7, so therefore that's to be found here. 6.48 is the cutoff point. We are above that, so therefore this becomes 7. Then we have, 13.987. Again, you can see that it's less than what it used to be because we made the standard divisor a little larger. So we have 13.978, lower quota 13, upper quota 14, cutoff points 13.491. We are clearly above that, so this will once again become 14. That's the same as last time. And then finally we have 5.464, lower quota is 4, upper quota is 6, lower quota is 5, upper quota is 6. That's to be found right here. The cutoff point is 5.477. We are clearly below that, so therefore this actually gets rounded down to 5. That would be a difference between what happened this time and what happened last time. So now when you add all of these standard quotas up, or rounded standard quotas I should say, now you are going to get 40 seats in Congress, and at that point you just stop. Okay, so that's how you do the Huntington Hill method. You find a suitable divisor. We started by trying 10,000, and when we did that and then we rounded according to the geometric mean, we ended up with too much. So then you had to bump up the standard divisor just a little bit through trial and error, get different standard quotas as a result of that, round those according to the Huntington Hill cutoff, according to the geometric mean, and then hopefully you end up with an amount of seats that add up to 40 in this case. All right, so that's how you do the Huntington Hill method. So that right there concludes the description of the various methods. We've gone over the Hamilton's method, the Jefferson's method, the Adams method, Webster's method, and Huntington Hill method. We also actually talked about the various paradoxes and flaws so far as well, new states and so on. That does leave Belinsky and Young, but before we move to Belinsky and Young, I would like to once again just kind of look at the flowchart and get a sense of it once again. So starting with the Hamilton method, we have the following steps. Calculate each state's standard quota, give to each state its lower quota. That's, very much a unique feature of the Hamilton's method. You give to each state its lower quota no matter what. You then give the surplus seats to the states with the largest residues until there are no more surplus seats. We talked about what residue means. That basically means the decimal stuff that follows the whole number. And you can clearly see from the Hamilton's method that it could result in various problems. And those problems would be the Alabama paradox, the new states paradox, and the population paradox. Let's look at the Alabama paradox. That says that when an increase in the total number of seats being apportioned in and of itself forces a state to lose one of its seats. So if you think about it, if you have, once again, 400 seats in Congress, and then all of a sudden that changes to 410 seats in Congress, it shouldn't be that one of the states loses a seat after you just increased the total number of seats. That would be a completely paradoxical situation, but actually it happens every now and then, and unfortunately it happens with Hamilton's method. Hamilton's method also might result in the new states paradox that says that sometimes when a new state is added as well as extra seats, it will cause a previous town to lose a seat, or a previous state to lose a seat that they had before. So sometimes if you add another state as well as extra seats, it's unfair for another state, one of the previous states, to lose a seat that they had before just because some new state comes in while adding extra seats to Congress. If it's the case that a new state is created and that causes a previous state to lose one of its seats in Congress, that makes it such that it is the new states paradox, and that would be unfair if it's the case that simultaneously we added new seats to Congress at the same time. Now, population paradox is another thing that can happen with Hamilton's method, according to this one. When a state with a positive population growth rate loses one or more seats to another state with smaller or no population growth rate, that is a paradoxical and unfair situation as well. Because think about it, if a state increases in population, why should that state lose a seat in Congress when some other state that doesn't even have a population growth, gains that seat? That makes no sense at all. But occasionally this does happen, and it happens with the Hamilton's method. And looking at the next method, which is the Jeffersons method, as a quick review, the steps are to find a suitable divisor D, lower it a bit, use D as the divisor, compute each state's modified quota. And the third step is to apportion to each state its modified lower quota. So once again, you are finding a suitable divisor for D. In this case, you're lowering it. And what that does is that bumps up the standard quota a little bit. It makes it a little bit higher. And at that point, then you round down in the same way that you would do with Hamilton's method to the lower quota. And each state is apportioned its lower quota. And you keep trying different potentially suitable divisors until you find a divisor that results in modified quotas rounded down in such a way that would total the total number of seats that you need in Congress. And unfortunately, Jefferson's method will occasionally result in upper quota violations. Jefferson's method would occasionally violate the quota rule, where basically it would cause some states to have more than their upper quota. Okay, and that's a problem. And the upper quota is the next integer that is above the decimal of the decimal value of the standard quota. So that's the Jefferson's method. The Adams method is such that you pretty much do the same thing, only you find a suitable divisor where you raise it a little bit, and then you find the modified quota. Now, the reason you'd want to raise it is to actually make the quota smaller, and then you would round each quota up to its modified upper quota. And the Adams method occasionally will result in lower quota violations where some states might end up getting less seats than their lower quota. That's a problem. Webster's method is such that you would find a suitable divisor, but now the rounding, unlike the previous two methods that I just discussed, you actually round in the conventional way, where once you find the modified quotas, you're going to have some decimal residues going on, and then you would round in the sort of normal way, and you would keep trying different potentially suitable divisors until you found modified quotas that would round in a conventional way in such a way that would total the total number of seats that you are targeting. Now, that was a very long-winded explanation of these steps here, but you could always just rewind the video to once again remind yourself what the heck I was just talking about there. Nonetheless, hopefully my student understands based on the previous explanation and that brief summary. So quickly, with the Webster's method, we want to look at what flaws are in Webster's method. And as you could clearly see from the flowchart, you have the occasional problem of violating the quota rule, and that would be upper or lower in this case. Okay, so for my student who's watching at home, that is the stuff that I would definitely memorize for the contemporary mathematics test. Things like that, the big picture stuff in particular, when it comes to not only what each method is in general, to have the general gist of each method, but also memorizing what violations and paradoxes each method might run into. Okay, so moving on to the Huntington-Hill method. This is the one that we just kind of went over in detail recently, and you may have noticed it's really the same thing as the Webster's method, except instead of rounding in the conventional way, you're going to be rounding in accordance with the geometric mean of the upper and lower quota. So very quickly, you find a suitable divisor D, you use D as the divisor, compute each state's modified quota, and then from there you find the apportionment by rounding each modified quota according to the geometric mean. That's when we brought out that chart from before. And to have a chart handy that lets you know the Huntington-Hill cutoff point will be very, very helpful. I had also mentioned that the Huntington-Hill method is the method used by the United States Congress. That is a good piece of trivia. I would not be surprised if that's actually a question on the test. And also, let's see. The Huntington-Hill method violates quota rules occasionally, the quota rule occasionally, where it might violate the upper or lower quota. Once again, to violate the quota rule is to have it be the case such that a state ends up getting an amount of seats that is more than its upper quota or an amount of seats that is less than its lower quota. Okay, so that's the quota rule violation. Okay, so that is a nice overview of the methods as well as the various paradoxes and flaws that each method might run into. And now let's move on to this Belinsky and Young part. And the Belinsky and Young part of this outline is basically just referring to the Belinsky and Young impossibility theorem. Okay, so we could say, I'll just write that. Impossibility theorem. The Belinsky and Young impossibility theorem. Okay, so what the Belinsky and Young impossibility theorem says is that an apportionment method that does not violate the quota rule, which by the way is right here, and does not violate or produce any paradoxes, is a mathematical possibility. So I'll say that again. An apportion method that does not violate the quota rule and does not produce any paradoxes is a mathematical impossibility. Another way of saying it is it's impossible to have a perfectly fair apportionment method. Okay, in the same way that it's impossible to have a perfectly fair voting method by which to determine elections, it is impossible to have a perfectly fair apportionment method if you wanted to define fairness as a method that would not violate any of this stuff. So literally, every method in the known universe and every method that we could possibly come up with in the known universe will violate either the quota rule or it will produce a paradox. That's just the way it is. All right. So that is the conclusion of this next section of the contemporary mathematics concept overview. Hopefully it was helpful. We do have one more video to go. I'd say this video is probably one of the more challenging and dense ones. If you hung in there with this one, I give you a lot of credit for that. The next one's going to be a little bit shorter and, in my opinion, a little bit easier to understand as well. So anyway, for my student who's watching, hopefully that makes sense. And as you know, you could email me with questions, all right, or text me with questions. And for those of you who are watching other than my students, good luck.